Imagine you wake up 10,000 years ago with nothing but a rock. No roads, no power grid, no server farms humming in a cold room somewhere in Virginia. Just you, the rock, and a mission that will take the rest of human history to complete. The internet isn't one thing. It's thousands of inventions stacked on top of each other, and every single one requires the last. Electricity, glass, chemistry, mathematics, cables on the ocean floor, buildings full of computers generating enough heat to cook you alive. Every piece has to exist before the next one is possible. None of it exists yet. You look at the rock. The rock doesn't care. You've got a long way to go. Step one is staying alive. You can't engineer anything from a grave. You chip the rock into something with an edge and use it to cut wood, skin animals, and dig into the earth. You figure out which plants won't kill you and which ones will, and you try very hard not to confuse the two. You get hurt constantly. Infections are a real concern when your medical supplies are leaves, but you survive the first winter, then the second. Slowly, you get better at this. You spend less time panicking and more time watching, more time thinking. That's the whole trick, really. Human progress has always been about buying yourself enough time to think. Right now, you don't have much of that yet. Eventually, you realize that pure survival is a dead end. If every waking hour goes toward finding food, nothing else ever gets built. So you become a farmer. You clear land, save seeds, breed animals for meat and labor. It takes years before any of it works reliably, but one season, you harvest more than you can eat. A surplus. For the first time, you have days where food isn't the emergency. You use that time to observe things. How water flows downhill, how fire behaves in wind, how heavy objects fall the same way every single time. None of this feels useful yet, but you're writing things down, scratching marks into clay, recording what you notice. That habit will matter more than almost anything else you do. One day, you pick up a rock that's heavier than it should be. Dull orange color, almost like dried blood. You throw it into a fire out of curiosity. Nothing useful happens at first, so you build a better fire. Hotter, more controlled, fed with charcoal instead of wood. You experiment for months. Then one day, something inside the stone changes. It softens. It flows. You've made copper. Then, by mixing different ores together, you stumble onto something harder. Bronze. Then iron. Each one opens a new set of doors. Your tools stop breaking. You can cut and shape things that were impossible before. The original rock that started all of this seems almost quaint now, but it got you here. Metal gives you better tools. Tools alone don't build the internet. You need to think precisely, which means you need mathematics. Not because it's interesting, because you need things to actually work. Counting leads to arithmetic. Arithmetic leads to geometry. You work out how to measure angles, calculate areas, predict where a stone will land when you throw it, then you push further. You develop algebra to solve problems you can't see directly. You work out the relationships between changing quantities until you've essentially reinvented calculus on your own. That sounds unhinged for someone who started with a rock. But here you are. You now have a language for describing how the physical world behaves. Without it, you can't design circuits, can't build lenses, can't do almost anything that's coming next. Now you need chemistry. The internet runs on glass. Specifically, fiber optic cables made from glass so pure the number is almost physically offensive. Regular glass has impurities that scatter light after a few meters. That's not going to work when you're trying to send data thousands of kilometers. You need to understand atoms, molecules, how materials bond and break apart. You start with the basics: burning, dissolving, combining. Some reactions release heat, some absorb it. You catalog elements, separate them, test what they do. Slowly, you build a working model of how matter is structured. This took generations of chemists in actual history. You're doing it alone, which is a problem, but you've been writing everything down. Those notes become your laboratory and your memory simultaneously. Strange things keep happening that you can't ignore. Rubbing certain materials together creates a spark. A lodestone pulls toward iron without touching it. Lightning splits a tree 50 feet away, and you stand there watching it for too long. You start paying close attention to all of it. You build early batteries, stacking metal plates with acid between them. A weak current flows. You test which metals carry it and which ones resist it. You work out voltage, current, resistance. Then you wire up a simple circuit and something strange happens across the room. A loop of metal connected to nothing sparks every time yours does. No wire connects them. You put a wall between them. It still sparks. When electrical charge oscillates with sufficient frequency, it generates invisible waves. They travel through air, through walls, through you, radio. That's going to matter later. But first, information needs to travel over distance reliably. You run a wire between 2 points and tap out a signal. On and off, long and short. That's the telegraph. For the first time, a message travels faster than a person can carry it. You spend years refining this. Faster signals, longer distances, better insulation, then you take it underwater. A cable across the ocean floor. This is harder than it sounds. Saltwater corrodes everything. Pressure at depth crushes poorly designed housings. Your first cables fail. You redesign them, coat the insulation in a natural rubber harvested from a tree in Southeast Asia, and try again. Eventually it holds. Two continents can exchange a message in minutes instead of weeks. That's the skeleton of what eventually becomes the internet. Now for the glass. You already know the internet runs on light. Pulses of light fired through fibers thinner than a human hair, traveling at close to the speed of light for thousands of kilometers. For that to work, the glass cannot scatter the signal. Each impurity absorbs a photon, and each absorbed photon is a piece of data that never arrives. Normal glass won't cut it. You need silica refined to a purity that seems excessive until you understand why it's necessary. You develop a process where you heat silica compounds into a vapor and deposit them as an ultra-pure solid, layer by layer, building a glass fiber that can carry a signal for dozens of kilometers before it needs any amplification at all. Then you build the lasers to fire into one end. The cable becomes a river of light. Here's where it gets genuinely difficult. Light through glass moves data, but something has to decide what data to send, to who, and in what order. You need computers. Computers need silicon. Not the silicon in beach sand, which is mostly silicon dioxide mixed with everything else. Pure silicon. So pure it makes the glass look casual. You develop a refining process that strips out contaminants one by one until you're at 11 nines of purity. That's 99.999999999% pure. A single misplaced atom can throw off an entire transistor. Out of that silicon, you etch transistors onto chips at scales measured in nanometers, billions of them on a surface the size of your thumbnail. Getting to this point alone takes centuries of chemistry, physics, and manufacturing precision that would have seemed like fiction when you were chipping rocks. The transistor is just a switch, on or off, 1 or 0. That's the whole thing. But when you stack billions of them and run them at several billion cycles per second, something remarkable emerges. You can represent any piece of information as a pattern of ones and zeros, any image, any sound, any text. Then you can move it, copy it, compress it, and send it across the world in under a second. The chip is the product of more collective human effort than almost any object that has ever existed. Photolithography, clean rooms where a single dust particle ruins a batch, chemical etching at atomic scale. You built all of that, starting from the rock. It's starting to feel like the rock was doing a lot of work. With transistors, you build memory and processors. RAM holds what your computer is actively using. Storage holds everything else. Processors execute billions of simple operations per second. On their own, these components are useless, but stacked with software, they become something else. You write operating systems that manage resources and keep programs from crashing into each other. You write programs that let a person interact with the machine without speaking in binary. Layer on layer on layer, each one more abstract than the last. A person typing a message has no idea what the hardware is doing below the surface. That invisibility is intentional. The complexity has to be hidden, or none of it is usable by anyone except the person who built it. Now you connect two computers with a wire. One sends data, the other receives it. Simple enough. But the internet isn't two computers. It's billions of them, all trying to communicate at the same time over different hardware, different distances, different speeds. You need rules that every device agrees to follow. A common language. You develop protocols. TCP/IP is the foundational one. Every piece of data gets broken into packets, each labeled with a source address and a destination address. The packets travel through the network independently, taking whatever path is available. When they arrive, they reassemble in the right order. If a packet gets lost somewhere along the way, it gets sent again automatically. The system doesn't need a central authority telling it what to do. It routes around damage on its own. That design choice turns out to be extremely important. Addresses are numbers, long ones. Nobody wants to type a string of digits every time they want to load a page, so you build the domain name system. Every website gets a human-readable name. When you type that name into a browser, a DNS server looks up the corresponding address and routes your request to the right place. There are 13 root DNS servers anchoring the whole system. They don't store every address. They know who does. A request cascades down through layers until the right server answers. The whole lookup takes milliseconds. You never notice it happening. The best infrastructure is the kind nobody thinks about because it never fails, and you built something that works so well, it becomes invisible. Most people picture the internet as wireless, floating invisibly through the air. The reality is mostly the opposite. About 95% of international internet traffic travels through undersea cables, hundreds of them, crisscrossing the ocean floor, connecting every continent. Each one carries terabits of data per second. You laid these cables from ships, unspooling them into deep water while managing tension, pressure, and current. When a cable breaks, which happens more than you'd like, you have to locate the fault within meters using a signal reflection technique, then send a ship out to drag it up from several kilometers down, splice the damage, and lower it back. It's underwater surgery performed blind. You do it because the alternative is significant portions of the internet going dark, and that's not acceptable. The data has to live somewhere, not in the cloud, which is a marketing term for someone else's building, in actual buildings. Data centers are warehouses filled with servers running constantly, generating so much heat that cooling them is a massive engineering challenge on its own. You build them near cheap electricity and cold water. You design precision cooling systems to pull the heat out before it damages the hardware. Some facilities submerge servers in tanks of non-conductive fluid. One company lowered a sealed container of servers onto the ocean floor and found the failure rate dropped significantly. Apparently, fewer people were around to make mistakes. All of it, every email, every video, every search, sits on physical hardware in a physical room somewhere on Earth. The internet is not abstract. It's a lot of very warm buildings. Between your device and those servers sits an enormous routing infrastructure. Internet exchange points are large facilities where different networks physically connect and trade traffic. Your data hops between routers dozens of times before it arrives anywhere. Each router reads the destination on your packets and makes an immediate decision about the best next step. Routers communicate with each other constantly, sharing information about congestion and outages, updating their maps of the network in real time. When a cable gets cut somewhere, the whole system reroutes within seconds. You don't notice. The page loads a little slower for a moment. That reaction speed is the product of the protocol design you built from nothing, starting with math, you invented when you were still trying to figure out how levers worked. Before any of this is actually safe to use, you need security. Sending data across a network you don't control means strangers can intercept it. Early internet traffic traveled in plain text. Anyone positioned between you and the server could read everything. That's not acceptable for anything sensitive, which turns out to be most things. Modern encryption relies on a mathematical asymmetry. Multiplying two large prime numbers is easy. Factoring the result back into those primes is computationally brutal, even for powerful hardware. Your device and the server agree on a shared key without ever sending it openly. The connection becomes private. Your browser shows a small padlock in the corner. That padlock represents a chain of mathematical guarantees, reaching back to number theory you developed centuries ago when you were still mostly doing geometry in the dirt. The last stretch is wireless. All those cables, all that routing infrastructure, all those data centers, and the final connection between your device and the network is a radio wave bouncing through your living room walls. Wi-Fi uses a specific band of the electromagnetic spectrum. Your router converts the incoming data signal into radio waves and broadcasts them. Your device catches the waves and converts them back. The range is short. Walls reduce the signal. Cell towers extend coverage further by blanketing larger areas in radio frequencies your phone automatically seeks out. Your device connects to whichever tower has the strongest signal and hands off to the next one as you move. Continent-spanning cables, hundreds of hops through routers, and the signal finishes its journey as invisible waves traveling 30 feet across a room to find you. Consider what you've actually built. Over 5 billion people use the internet every day. At any given moment, millions of video calls are happening simultaneously. Streaming services push terabytes of data per second. A single search triggers hundreds of server queries in under half a second. Stock trades execute in microseconds. Weather sensors on every continent send real-time data constantly, all of it running on hardware that didn't exist 10,000 years ago when you were holding a rock and hoping something ate the deer before it ate you. The scale is almost impossible to hold in your head. More information moves across this network in a single day than all of recorded human history contained before it was built, and it mostly just works. Think about what had to go right. No metal without fire, no circuits without metal, no chips without chemistry, no protocols without computers, no internet without all of it working together simultaneously. You invented or reinvented mathematics, physics, chemistry, electrical engineering, materials science, computer science, and global telecommunications infrastructure. You laid cables across ocean floors and built rooms that have to stay running every second or something breaks. You designed systems that reroute themselves when components fail, encrypt data without slowing it down, and scale to billions of users without requiring anyone in charge. Every person who ever worked on this was building on everything that came before, including you, standing in the dirt 10,000 years ago, holding a rock and looking up at the sky. And now that the internet exists, You can use it to watch videos about how the internet was made. You can look up any fact, contact anyone on Earth, access more information than you could read in 1,000 lifetimes. You can order food without speaking to anyone. You can watch 16 hours of television without moving from one spot. You can argue with strangers about things that don't matter and will never be resolved. The infrastructure you spent your entire civilizational history building, the cables and chips and protocols and data centers, all of it now pointed at this exact moment. Someone, somewhere, is using the world's most sophisticated communication network to watch a raccoon open a jar. The rock started all of it. Hard to be mad about where it ended up.